got her bachelor's degree in mathematics from LSU and PhD in statistics at UNC Chapel Hill, working with PK Sen. She then moved to Penn State, where she started her academic career, and she was there until 1998 when she moved to Michigan. Susan has a long list of publications and activities, which I won't go into. They would make all of us look small by comparison. She's very active in the community in a wide variety of roles. She's a fellow of IMS and ASA, an elected member of ISI, and of the Institute of Medicine. She was recipient of 2013 MacArthur Fellow Genius Award. She's only the 5th statistician to receive this honor. And just for your information, the others are Peter Bickle, Percy Diaconis, David Donahoe, and Brad Efron, which are not too shabby. That's pretty good company to be in. Her current research interests include causal inference concerning dynamic and individually tailored treatment regimes, sequential decision problems arising in the design of dynamic treatment regimes and mobile health intervention, and inference for high-dimensional models. Please join me in welcoming Susan.
Thanks so much for this introduction. I really appreciate it. So the work I'm going to talk to you about is work that I've started. It's more recent work, and you can really have an impact on the direction I go. I'll listen carefully to your questions. You'll see there's a lot of open problems in this work. Oh, I wanted to talk about Ralph A. Bradley. I got the chance. Actually, I should turn this on. Can you hear me? Yeah. I got the chance to read his the statistical science and I highly recommend reading this article. It's an extremely entertaining article. It turns out that both he and I both went to UNC. I was very excited, so he's like a brother in some sense. And even more importantly, he got to meet H.E. Robbins, who, if any of you have ever met Professor Robbins, he has a very distinct personality. And Ralph relates some of the things that Robbins did in this statistical science paper. Very interesting. He didn't even know he had a thesis for a while there, because Robbins got in a big argument with some other person on the committee, and they forgot to tell him his thesis was okay. So it's quite interesting. One thing that was really, for someone like me, the thing that was so impressive about Bradley, I mean, really impressive, is this is a guy who, he was very active, just like most young people are, and then he became chair for quite some time. Then he became president of the ASA. And you would think, okay, most people at that time, they're going to rest on their laurels, right? I mean, that's what most people do. But if you look at his publication records, you see that this is someone who, after all of that, published some really nice papers and very influential journals. It's quite impressive that he just didn't sit down on his laurels and wait for, to retire or whatever. It was very impressive. Okay, so the group I'm part of, we have this overarching goal of designing what we would call a continual learning global health intervention. And I'll talk to you a little bit about this. This is part of modern day sequential analysis. You'll see some elements of that here, but it's not as overt as it would be with other aspects of the problem. And I'm going to make the topics concrete, I'm going to carry through this example of heart steps. This is a mobile health intervention that we've been working on. It's going to go into the field in the next month. It's for individuals who are sedentary. We have a whole series of studies that we've been funded to run concerning this intervention. And it has sensors on a bracelet. They detect your activity level, the quality of your sleep. And then we have an app on the phone, and a variety of sensors are on the phone as well. And what we're going to focus on today is a particular type of trial design. It turns out this is a first thought how we might conduct experimentation in this setting, and I am positive someone can improve on this. So what kind of data do you get when you think about a wearable device that can both sense and sense information on you and provide interventions. You can think of it in terms of a time series for each individual. So we call it the state. S denotes the state. This is the information we have at the J decision time, SJ. Then we have action, which is usually a treatment in this setting. And then we have a response. We're calling it a proximal response. To a statistician, this is more like a time-varying response. The state, I use the word state to get you to think of a Markovian type setup, and that's often the way people are thinking. So state is not only what you measure right now, it can be summaries. For example, in alcohol addiction, it might be volatility and craving over the past day. So state can bring it involves not only information today, it involves summaries of the past history of the individual. In a sense, it's a modeling type assumption. What information do you need to put in the state so that you have a Markovian type state? The decision time. So usually in this setting, there's two flavors for the decision times. You see both situations where there are regular intervals in time. These can be very dense intervals in time. For example, going back to the alcohol addiction study, here they were monitoring people to see when they would come within 10 meters of where they usually bought their liquor. And if they came within 10 feet of where they usually bought their liquor, the phone would alert them. So in that case, the decision times would be every, say, 2 minutes or so, because you have to alert the person before they make it into the liquor store, right, to be useful. And the other type of decision time you see in this setting is at user demand. This is pretty common in the mobile health field, is that there's a button on the phone that you can press and you can request help. So you're really stressed out, you press the button and it reminds you of a behavioral therapy that you've been engaged in and how you might manage your stress. So it's connected to some therapy that you're already in. Heart Steps has two types of decision times. We don't have this at user demand, not yet anyway. The first is a momentary decision time, and this is every 2 to 2.5 hours. It turns out that's around 5 times a day. And the reason why those decision times, these 5 times are chosen, is because the bracelet that I showed you on the past slide, this is from Jawbone. We had access to hundreds of thousands of their users. And when sedentary people, if they are active, they tend to be active at 5 different times of the day. Before they go to work, around noon, mid-afternoon, when they're coming home from work, and after dinner. So those are the 5 times that we're talking about here when I say the 5 times. There was also a decision time each evening. We'll see an example of that shortly. The state, there's 2 flavors for the state, how it's collected. There's both passive information that's collected, how busy your calendar looks, so your Google Calendar on your phone. How busy does it look over the next couple of hours? Where are you right now? Are you at home or are you at work? The weather, is it bad or is it good? Is it raining and so on? We don't use social context, but that's pretty common to use social context. Are there other people around you? And then there's also actively collected data. The trend now, so actively collected is where the phone pings you and asks you a question and you have to answer it. The general trend right now in mobile health is to eliminate as much as possible actively collected data. And there's some really interesting statistical questions concerning actively collected data that I could talk to people. You want to, I can talk to you about it later if you think you might be interested about how you can minimize the active collection of data in the setting, yet have high quality inputs. Heart Steps includes activity recognition. We know we have a classifier built in that classifies whether or not you're walking, driving, standing, sitting. We know the weather, we know your location, we know how busy your calendar is, we know your step count, we know whether or not you've been accessing Facebook or not, we know a lot about you. And in the evening, we do get some actively collected data concerning how the day went. Art Steps is a 42-day study. It's the first of 3 studies, and it's the shortest of the 3. The actions, so there's a whole variety of actions. I just listed 2 here, but one is the kinds of treatments you can provide at a decision time. I'll give you some examples of that shortly. And then whether to provide a treatment. So in terms of the kinds of treatments, when I first got into this area, I thought, there's not much you can do with a phone. I mean, give me a break. I mean, it's a phone, you know, what kind of treatment can you provide? It turns out there's an enormous variety of interventions that can be provided by the phone. Some are behavioral. So there are ways for you to change your behavior. So maybe you need to avoid a certain location, like the liquor store. Or you may have a substitute activity. Instead of smoking, go take a walk. So the behavioral types of interventions. Then there's cognitive interventions where you rethink things. Suppose you're trying to quit smoking, you slip up, you have a cigarette. How do you rethink that so that you stay on task? Other interventions are motivational interventions so that you keep going. Most of the areas in mobile health are areas in which people are really struggling long-term with behavior change. Losing weight, healthy eating, managing your diabetes, managing your high blood pressure, managing an addiction, and so on. Other types of treatment are social treatments where you involve significant others. You have automated text messages to a partner or to someone who's a mentor who can come and help you and contact you. We're going to focus actually on whether to provide a treatment. My gut feeling is most of the signal is probably there. And the reason why it's going to be, a lot of the signal will be there is because the burden associated with being, when you have something that can provide, that can ping you in your real life, in the context of your life, the burdens can be extremely high. We're going to have there's 2 types of treatments. The lock screen recommendations, these are little suggestions. I'll show you an example of what you could do to be more active. And then this is planning your next day, planning your exercise the next day. The 2 blue areas are what we're going to focus on. I will show you an example of the daily activity planning just so you have a feeling for what it looks like. Okay, so here's the one I want, the daily activity planning. There's 3 options we have. We won't bother you at all. That's a very important option in order not to aggravate you. Then we have the option of where you choose something from a list. This list is populated by you and some standard suggestions, and as you make suggestions, it gets populated more and more by your ideas. Or there's just an open area that you fill in. And this is about what you're going to do tomorrow. What's your plan for being active? So tomorrow when I get to work, I'll take the long route to the office. So it's very simple things. These are for sedentary people. Every time I get on the phone, I'll walk around to get steps. So this is the intervention we're going to focus on. Remember, it can occur up to 5 times a day. There's 5 different times before you're at work, midday, and so on. And this is a 42-day study. So we'll either we're not going to bother you at all, nothing happens, or you get a message on your lock screen. So your phone lights up, it pings, and you get this type of message here. It's with all your other notices. So this one, these messages are tailored to the weather. This was on a cold day. It was on a weekend. And it must have been around midday or mid-afternoon, I think. They're tailored to the time of the day. So we're not going to suggest you go walk outside if it's raining, for example. You see, you can dismiss this message, you the user. You can press thumbs down and the message goes away. You like the message. You can press thumbs up and the message was useful too. Or you can press this little bell thing. It's kind of like a snooze button. If you press the snooze button, a drop-down menu comes out, and you can snooze, you can turn off the intervention for 4, 8, or 12 hours. So like if I'm going to an NIH, I've been testing this for months and months. So if I go to an NIH review committee meeting, I just go in, I snooze it for the next 12 hours in the story. So you can do that. The response, as I said, it's a time-varying response. And these actions the most part, these treatments, they're intended to have a proximal effect on your behavior. So if you're experiencing a lot of craving for a cigarette, it may be an intervention that tries to help you surf through or manage that craving. Or for you to walk around a little bit. Like I've gotten interventions with the heart steps where it said, why don't you just stand up and roll your arms around? You know, so it's trying to affect you in the very proximal way. So the why tends to be a proximal outcome. And in heart steps, it's going to be how many steps you took over the next 60 minutes. Up to 5 times a day, how many steps you took over the next 60 minutes. Okay, I wanted to just go over our group's scientific goals. I think it's safe to say that we have an agenda that's going to last us about 15 years. And this area of mobile health is completely open from a statistical point of view. I mean, we have not been here at all, we the statistical community, and there's enormous problems that need to be dealt with. So what we're going to talk about today is how we can collect data that we can even say whether or not those treatments are having an impact on the proximal outcome. I mean, that's the first question you want to ask. Did the treatments have any impact at all? Another question, though, is often you want to know, do the treatments have some sort of delayed effect? They may very well, by inducing burden, then you begin to ignore further treatments. And you want to know if maybe it's better to provide little treatments in the morning for me, but for him, it's better to provide little sedentary activity messages in the evening, right? So we want to know in what context should we provide these messages. That's another thing. We're also working on decision rules that input all the information and output whether or not. So matching whether or not we provide an intervention to you at that time, to the setting that you find yourself in, whether you're at home, whether it's a weekday, whether it's a weekend kind of weather, and so on. And then lastly, it looks like we're going to have funding for this. We're developing from a statistical point of view. This is actually sequential analysis. It's a stochastic approximation policy that continually updates how you match the context to whether or not you provide an intervention. We're going to do the blue today. And actually, I have to be honest, I just want to, for the students in the audience, this was something that bothered me a lot. And this is now the second time this has happened to me. I get really excited in a problem, and I want to just do this, okay? This is all I care, because this is where the cool computations are. This is where the cool statistics. I mean, let's be honest. I mean, this is what I'm thinking in my head. I want to do this. I took a whole sabbatical. I spent all this time with guys who work in artificial intelligence, just so I can work on this problem. But then I start to think, and I realize there's a whole set of things that must be done to set the stage so that this has any impact in real life. And I have no options. I must do those things. They must be done. And this one must be done. Designing a trial to even assess whether or not you have an effect on these actions. So what we're calling these trials, we're calling them micro-randomized trials because there's many randomizations. See the similarity? So each person can be randomized hundreds or thousands of times. So this is a 42-day study, 5 decision points per day, 210 times. The last study that we're to run is a year-long study. And I'm not sure how many decision points we'll have, but they'll probably be randomized thousands of times each individual. I believe I'm going to call these sequential full factorial designs. So I just want to say, if you're used to experimental design, it's very different. What's going to happen here is we're going to have main effects. Our treatments are time varying, so our main effects are going to be time varying. And if we start looking at interactions, we'll have interactions that are time varying, right? Okay, I'm preaching to the choir here, but this comes up time and time again. People say, well, look, I don't want to run a randomized trial. I don't want to do any kind of randomization. Because what I'll do is I'll go to, like, Jawbone or one of the other, like Microsoft, and I'll get information on tons and tons of users. I'll see how they use the device, and from that, I'll figure out whether or not the interventions work. End of story, right? And so why, this is all about why we should do randomization. The first thing is, we all know factorial designs, not 2-arm randomized trials, not 3-arm randomized trials. Factorial designs are the gold standard if you want to form a multi-component, a multi-factor intervention. And that's what we're talking about when we talk about a micro-randomized study. It's for the purpose of building an intervention, not for the purpose of evaluating an intervention. Randomization is the gold standard for providing data to assess a causal effect. And fundamentally, that's what we're interested in, right? Whether or not these treatments really impacted your activity. It turns out the randomization will enhance the quality of, this is going to be a setting where the primary data analyses will be enhanced by the randomization. But then there's going to be a whole host of secondary data, further data analyses that will build on that randomization. So what we're going to talk about today is how we can justify or form a sample size. How many participants do we need in this study? And we're going to focus on the momentary lock screen message, the one that kind of occurred up to 5 times a day. And I'm thinking in the back of my mind factorial design. And this is coded 0. We provide a message. 1, we don't. These are tailored messages, but still. No message. And of course, I want to randomize it probably 1/2 because I'm a statistician and I know if you use 1/2, you get higher power to detect an effect because half your people get the intervention, half don't, at any given time. It seems like that would be a really good idea. It turns out that's not going to work in these settings, and it's really not going to work in mobile health. And the reason why, again, it goes back to that burden issue. This is something you're carrying around day in, day out. It's with you all the time. And you cannot bother people too much, or they delete the app. In fact, most mobile health apps nowadays, the kinds you can download from the Google Play Store or from whatever Apple has, the Apple Store or whatever, they're deleted within a couple of months. So to a large extent, the burden imposed by these is significant. So the guys who are working on this, they said, look, we want on average 2 a day. So 5 times a day. How do we get an average of 2 a day? We do 40% probability that you get the intervention or not. And we're going to determine our sample size to test whether or not there's a proximal effect. That is on the activity level. In the case of heart steps and another problem, it would be a different kind of effect. Okay, so I'm going to now go through a number of, there's going to be a number of really subtle points that I really want to make sure I'm being clear when I explain them. And a lot of them are going to be related to this notion of availability. And this is something I did not want to deal with. When I came to this problem, I wanted us just to ignore this issue altogether. And again, getting back to that burden issue, this is really important. And it makes the problem, from a statistical perspective, incredibly interesting. So it actually makes it better for you and me, but nonetheless, yeah. Okay, so you can only deliver a lock screen message when the intervention is on. You can't deliver it when it's off, right? This intervention, in heart steps, for example, if we classify you as driving, we cannot ping you and ask you to look at the lock screen. We get in trouble with the IRB. Ethically, it's inappropriate. We can also, if you're currently walking around, we can't ping you and suggest that you walk around. That just does not make scientific sense. Again, you're unavailable. So if you're classified as walking around, we can't ping you. And lastly, if you've turned off the intervention, we can't ping you. In a sense, you removed consent. You said, look, I'm not here. Don't bother me. So you can, in the case of heart steps, there's 3 reasons why you might not be available. You're driving, you're already being active, or you've turned it off because you don't want to be bothered. So we're going to always have this variable I equal 1 if the intervention is on at a particular decision point, and it's 0 otherwise. So we can always randomize at that decision point, but we're not going to act on our randomization unless I is equal to 1. which means the intervention is on. Think about this. Now we're talking about factorial design with this variable. Okay, so to make things really, okay, so this may probably reflects my background, because I'm not coming at this from experimental design, I'm coming at it from, I have this background in causal inference. And so how do we, in causal inference, make our estimands precise? Potential outcomes. And that's what I'm going to do here. So what I'm going to put a bar on top of a letter just to mean the vector up to that point. So AJ is just all the actions up to that point. Capital letters are random variables, lowercase letters are realizations. These actually, in our case, this is just a sequence of zeros and ones, 2 to the j, different types of sequences. So I'm going to define my proximal response. Remember, it's our activity in the next 60 minutes. It's a function of all the actions that you may have gotten prior up to that time, right? It could be. Now, I'm being a little sloppy here because you only really receive an action if you're available. So you have to understand that when you see this. So if you were never available, you wouldn't have none of these actions would be closed. So this is the observed response if your actions are equal to this sequence of zeros and ones. And we have to do the same thing for the availability, because you and I both know that it could very well be that the amount of treatment you've received up to now could influence whether or not you say you're available right now. One reason could be that I've really bought the Kool-Aid and I'm walking every time. At each of those 5 times, I'm already moving because I'm on, so you're not going to be available then. Or it could be that you've aggravated me so much, I'm turning it off, right? So availability is also a function of how you were treated in the past. Notice the big difference between these two types of potential. So there's an activity level for every 2 to the j kind of pattern of treatments. There's an availability for every pattern of 2 to the j minus 1. So availability is only impacted by past treatments, whereas your activity is also past and present. Okay, so the proximal main effects, we have to define this, and we're going to use these potential outcomes. So we're defining it as the difference between my activity and following decision point j. Here I get a message, that's why it's 1. Here I don't get a message. This is a typical main effect in the following sense, and that I'm averaging over the other treatments. That's why I have a capital A here. These are the randomizations. The expectation is averaging over the past treatment. And any other treatments, like the evening, if there's an evening treatment, it's averaging over that. So it's like a main effect. In factorial designs, we're used to the main effects being averaged over the other factors. That's quite familiar. However, it's not familiar in the sense that it's conditional on you being available. That's where it's different from being familiar for us. It has both a marginal character in the sense that it's marginal over other treatments, yet it's conditional in the sense that you have to be available, or I am not interested in what your reaction would be to a message, an activity message, when you're unavailable. That's not assigned to me question. Okay, so it has both this marginal and this conditional characteristic. I want to talk about another aspect of it. We're answering this question right here. So let's think about as the study proceeds, that is j, time, as the decision points progress in time. So you and I might think, well, at the beginning of the study, everybody's confused, they don't even know how to operate their phone, they're barely getting it together, they may not have any impact on the message. Right? At the beginning, very low impact. But then rapidly, they're going to get excited, and so if they get a message, they'll become active. If they don't, they might not be active. So you might expect that this proximal main effect as j varies, might start off low and then get higher. And then what's going to happen? What's going to happen is everybody's going to get bored. They're going to get aggravated. It's not going to happen. So what could very well happen is it would start to decrease. I mean, That would be the worst case scenario, is that it would just get worse. It would have less and less effect as time goes on. That's one reason why you might have a time-varying trend. It's because the effect of the intervention will change over time. It'd start off kind of low as people get used to it. They really pay attention, they get some effect, and then they no longer pay attention. Another reason, though, is because of the people who are available at each time. So the population of people who are available is changing with time. So at the beginning of the study, you might have, most of the people may be available. But then as the study progresses, the people who have really bought into the whole game, they're less available because they're already being active. And the people who are really aggravated are less available because they've turned off the intervention. So the main effect can vary for two reasons, both because the treatment among the people who are available itself is varying, as well as the kinds of people that we're treating. And that's why it's absolutely critical that this is a time-varying effect. Because at each time point, you're talking about a different subpopulation of available people. This is a causal effect. It's an effect of giving among people who are available at the time. What's the effect of giving an intervention versus not? Okay, we're going to randomize. And so when we randomize, that randomization does is that if you're accustomed to the language of causal inference, it allows you to go from potential outcomes to the data you actually observe. And indeed, that's what I'm writing here. Because of the randomization, we can now write this difference here as the conditional mean of y, given that you're available and you've got treatment, versus the conditional mean of y decision time j, given that you're available and you didn't get treatment. And I'm going to call that beta j just in the next slides. So this is a time-varying main effect. So what we want to do is we want to size the trial. That is, we want to figure out how many people should be in the study so that we can try and see, is there even an effect? At any of these populations, does it make a difference? If for none of these populations, none of these availability populations, it makes no difference whether I give you a message, then there is no purpose in running with this type of an intervention. So we'll be interested in whether or not this is zero. This is a causal effect. Is that I've given this talk now a couple of times, and this is always a sticking point for people. Is among the available people, we randomize you to either get the intervention or not. So it's a causal effect among the available at each time j. Oops, went the wrong way. Okay, so how are we going to, so if you want to size the study, you have to form a test statistic, and that's how you back out your sample size formula. And the way we're going to do it, I'm going to take a time-honored approach. I used to work in toxicology when I was a grad student, and we used to do this sort of thing. So I'm going to use some ideas from a long time ago when I was in toxicology. What I'll do, remember J goes from J4 to 210 in hard steps. In other studies, it may be even higher. So what I'll do is I'll specify an alternative that I'm interested in detecting, and I'll form my test statistic based on that alternative, and I'm going to gain a lot by doing that. You're going to see. Okay, so in hard steps, the alternative I'm going to look at is a quadratic. This is pretty common in exercise studies, that you see the impact of the intervention increases at first, it levels off, and then often it goes down. It's a quadratic, and what these brackets mean is it takes the decision time on the 5th day and it turns it into the 5th day. So it's averaging over all the decision times within each day. So it's a quadratic over days, and just averaged over the effect within a day. Now you and I both know, in all likelihood, the time of the day is going to probably be important. And we can look at that in subsequent analysis, but for the primary analysis, we'll just average over that. The great thing about acting as if it's a quadratic, no, we're not acting, I should be really precise. What we're going to do is we're going to size the study so that we can, this will be the null. And we're going to try and focus our power on detecting this kind of alternative. The great thing about this is now we've gone from 210 parameters to 3 parameters. And in toxicology, what we used to do, these were dosed against toxicity, and we actually, that curve was usually, the curve was normally a curve that would look like this. It would curve up and then flatten out. So in that world, we always just used a linear function, because that's how you save your degrees of freedom. You only use 2 degrees of freedom then. Now, of course, you're not fitting the curve. That's not the point here. Remember, we're testing. We're doing a hypothesis test. We're not trying to fit a curve. We're doing a hypothesis test. So if you can save degrees of freedom and not cut your throat, you do that. The only reason I went quadratic here is because I'm so concerned that people are going to get overly burdened with this intervention. And by the end of the 42 days, it's not going to have any impact at all. And if it's a quadratic and it goes like this, and I fit a linear, it'll be a disaster. So I wanted to be able to allow myself to see that downturn. Actually, we have 3 studies now that are going in various areas of health that are going to be using this design. And if I'm not going to see downturns, you'll see me in a year or 2, and I'll just do a linear. I'm not going to waste my degrees of freedom on this. I'm going to only get 2 degrees of freedom. Our test statistic, we have to form a test statistic because we have to back out our sample size. And the way we're forming the test statistic is we're modeling the mean of Y, given the person's available, and whether or not they get a treatment. We have a time-varying intercept, a time-varying effect, and then we standardize in our case, we standardize essentially we're using, I think we call that contrast coding in experimental design. Except now it's not contrast because we're not randomizing 1/2. This is 1.4. So I'm centering and the gain of this, I'm sure people in experimental design, I think you might know this, if you center your treatment indicator, which is what I'm doing here, then the statistics will be, the inference on beta will be robust to how you parameterize this term. So you gain robustness. You'll still have consistency, and you can consistently estimate the variance of the estimator here, even if you have this wrong. It's not, it has higher variance, of course, but so there's a lot of gains to centering. What I'm doing is I'm making the matrix, the model matrix orthogonal. I'm orthogonalizing. That's what's going on. Turns out there's some other ways to do it, and I don't know which way is best. So there's a whole open area of how you should orthogonalize this matrix. But, I'm just being repetitive here. Okay, so our test statistic. Oh, okay. So I wanted to tell you how we're going to fit this. What we're going to do is we know that we have correlated data over time. I mean, it's obvious, right? But we're going to ignore that. Think like a GEE. Remember generalized estimating equations from the dark ages? So, so we're going to just do, we're going to, from when I was young, Nicole wasn't born. Anyway, so we're going to just fit, we're going to pretend like we have independent observations. Of course, we'll have to adjust the covariance. The variances will have to be adjusted, but we'll get consistent estimators. And we have our quadratic form in the case of heart steps. In other settings, this may be different. And we'll have some parameterization for the time variant main effect trend. Okay, so to be able to think even about how I'm going to form my sample size calculator or my formula, I have to think about my alternatives, and this is traditional. You take your parameters. Remember, we have an intercept, a linear term, and a quadratic term, so we have 3 terms, and we could think of them in a standardized world. So on standardized, D is the standardized effect, and sigma is the standard deviation. I'll give you the definition on the next page. And so we're going to elicit from our collaborators what the standardized effect. So we'll always think in terms of standardized. And I'll show you how we'll do this, how we actually did it in heart steps. The variance is just the variance of y given availability and reaction. So it's just an implicit assumption of constant variance. But we don't analyze the data that way. Just okay. So how we, in the case of hard steps, in which we use this quadratic to form our test statistic, the way we elicit the standardized effect sizes is we first ask them, what do you think the effects is going to be on the first day of the study? And I tell them they think 0. And they say, okay, we think 0. So this is 0. We always say this is 0. I mean, if this is conservative, I'm a statistician, right? So our role is to be conservative. And then I ask them, over the average, over the entire study, what do you think the average effect of the intervention will be? This is something they're used to thinking about, at least in the exercise field. So they'll give us a number, an average effect here. What they think, it's usually like 200 steps or something like that. And then I'll ask them, what day do you think the effect will be maximal? And from then on, it'll plateau off, or it'll unfortunately might go down. And they can usually tell me that too. So once they give me these 3 pieces of information, I can just back solve for the D's. The test statistic, it's going to look like a GEE test statistic. It's very mundane. I don't want to bore you all with that. It just, the model matrix X, the last 3 columns are going to be the intercept term for the main effect of the treatment, the linear term, and then the quadratic term. So it's exactly like one would think in this setting. The test statistic looks like a test statistic in the generalized estimating equation world. This isn't a GEE test statistic. Okay, it's really important to realize that it's not. Availability is changing with time. Availability is affected by past treatment. It's not. This is not a GEE type analysis, but it looks like it to a computation. So you get a quadratic form, and the term in the middle is the usual sandwich estimator that we've all studied probably in beginning statistics somewhere. And K is just a matrix picking out the right columns so that you get the right covariance. It turns out under standard moment assumptions, people have known, this is all, you can use the usual theory for GEEs. There's nothing going on here. Under our alternative of quadratic, where we have the standardized effects of D0, D1, and D2, the intercept, linear, and quadratic terms, it's just a chi-square with a non-centrality parameter. So, what's the message? To size the study, I just need to have some guess of what this guy is, and from that I can tell you what this number is. That's the message. And what we do here is we make a number of simplifying assumptions to simplify this term in the middle, and then we'll assess whether or not our sample size is robust to those assumptions. So the assumptions we make, we essentially act as if we have our model is the right model, mean 0, it has constant homostochastic variance, and we have independence in the errors. We make a lot of assumptions that these are all working. I say they're working assumptions because when you do the test, you don't make these assumptions. This is only for sizing the study. Under these working assumptions, that center term in our sandwich estimator, it depends only on the polynomials in time, the marginal distribution of availability across time, so we're going to have to think about that. And it depends on your randomization probabilities, how you do it. It does not depend on that that gamma J term, the time trend, which is great. That's the robustness, that's why we orthogonalize the model matrix. Okay, here's the next subtle point. Can everybody just stand up? I want everybody to stand up. We're going to have an intervention sedentary. Okay, let's just turn around. Just turn around. Just turn around. Just turn around. Turn around. Turn around. Okay. Okay, now you can sit there. That was an intervention, by the way. Luckily, you don't have a phone that's pinging continually to do this intervention. And you would understand why these things are so aggravating. No, okay, so the sample size calculation, it turned out I did not understand something about this sample size. Now maybe some of you who are used to doing a lot of applied statistics really will anticipate this, but I did not anticipate this at all. And in fact, I told the student quite a few times to reprogram everything. So what's happened here? What we did was we formed a test statistic based on that quadratic parameterization. Of course, under the null, our test statistic is valid, because under the null hypothesis of no effect at all, our test statistic is perfectly fine. So we're fine, right? But because we formed that test statistic in that way, we're not only using between-person contrasts and the proximal responses, we're using within-person contrasts of the proximal responses. This means that we're going to get very small sample sizes. I'm going to talk about this some more. Let's just say that on the first day of the study, the first time we randomized, we know 40% of the people are going to get a message, 60% aren't, right? So if I wanted to just size the study for that comparison, you would say, oh, Susan, it's a 2-arm study. 40% of your people are in 1 arm, 60% of people are not. Then if I wanted to do that the next time, I'd have another 40%, 60%, 210 times. So multiple comparisons here, right? 210 times, 40% in, 60% out. So I'm going to need a vast sample size because I'm just doing between-person contrast in the response. However, if I tell you I know a priori that all the effect of the treatment is the same all the time, then you would be able to do completely, you'd only need one person. And you just look within that one person. Sometimes you gave them the treatment, sometimes you didn't, and you just look at the difference in activity within that one person. You need only one person. Great. If I told you that. Of course, I'm not doing either one of those. I'm going in between. So I'm both getting some information by contrasting responses between people, but I'm also, because of that quadratic, this assumption, this working assumption of smoothness across time, I'm also allowing you to get information from one person when they get an intervention versus when they don't. And it's because of that quadratic trend over time. Quadratic trend. I'm telling you, that student suffered really bad. I've now learned, actually, most of the time when this student tells me something is the way it is, that he's right and I'm wrong. So now he doesn't suffer quite as much. But the consequence of this is when you start even doing your sample size calculation, this asymptotic business is not so hot. You really have to think about small sample approximations. And luckily, in the GEE world, this is a very mature field, extremely mature. People had already developed all these small sample approximations. We just lifted it from their work. And so one thing is to use a type of, it's related to Hotelling's T-squared statistic, if you're familiar with that, instead of the chi-square. Same in non-subtracting parameter. So we're going to use this to determine the sample size. So in the case of heart steps, of course, as always, on the first day we say we have no effect. I'm going to output a whole variety of average proximal effects on activity. And then we said a little bit over halfway through the study, we're going to start getting a decrease in activity, responsivity to the interventions. Our model is exactly what I told you. We actually use the same quadratic marginal over day, within a day, for both the day trend as well as the main effect of the intervention. Okay, here's our sample sizes. So you have to guess availability as well, and in this particular table, it's constant, approximately constant availability. Oh, this should be an I. So this is 70% availability or 50% availability. And here I'm giving you average standardized proximal effects. So this is number of standard deviations as a result of an intervention message. Okay? Now, if you have ever been involved in the health field, or even in psychology, for example, you'll know that these effect sizes are astronomical. For example, in the health field or in the behavioral sciences, a small effect size is around 2.2 standard deviations. This is really, really small here. The thing is, we don't know in the field of mobile health what reasonable effect sizes are. We don't have that kind of information yet. So it could very well be that these are massive effect sizes. We just don't know. So I provide a variety. Also, again, you see, so if a person is 70% available, around 33 people you need, very, very small sample, just strikingly small. If they're around 50% available, you need 43 people. Our study is going to have 40 people. The primary data analysis, I'm being completely repetitive. I think this is the exact same slide I used before. It's just that GEE analysis, and we're going to have that sandwich the quadratic form with the sandwich estimator, just like before. But now we're not making any of those working assumptions that I showed you. Here's your GEE statistic. Oh, again, once again, you cannot use large sample theory. So we're going to use that F statistic. Not only that, though, you have to adjust the sandwich estimator. And this is well known in the world, in the field of GE, that you have to adjust the sandwich estimator if you have a small sample. And we do that. You adjust it using the hat matrix of your view. This is all well known. It's not, this is not science on my part. I just wanted to show you some simulation results just so you have a feeling. So like here we're sizing the study for different average proximal effects, and you see the sample size in parentheses, and then you see the power to detect the alternative for that particular average effect. So again, this is only differing from 0.8 because of the Monte Carlo error. Actually, I'm not showing it to you here. I don't want to show you slides and slides of numbers. It's not very useful. But I want to just go over, as you can well imagine, because we simplified everything and formed the test statistic by using a quadratic, we were quite concerned about robustness. And we made a lot of working assumptions to get the sample size. So I'm going to go through where the procedure is not robust. First thing, if you tell me that the individuals are going to be available 70% of the time, and in fact they're available 50% of the time, we're going to get really bad power. This makes perfect sense. If you guess the average standardized proximal effect, if you guess it too high, you say, oh, we're going to have 0.2 of an effect, and in reality we only have 0.05, again, really bad news. So that was pretty much expected. We expected to see poor performance if your guesses aren't conservative. The thing that we did not expect is it turns out that if the variance of your activity when you're provided an intervention is really different from the variance of your activity when you're not provided an intervention, then we go from like 0.8 to 0.75 or 0.74. So there's a reduction in power, and we still don't know quite why that happens, because the sample size calculator is robust to all heterogeneous variance, delayed effects, interactions. That's not surprising because it's more of a factorial design. And so it's robust in a whole bunch of dimensions, but that one area is less robust. Again, we've gone over number one, and so I just want to, so this is a typical area of causal inference, except it's in high dimensional because our state variables, remember I talked to you about the state variables. It's everything your phone is sensing on you and all the wearable. So we're also running a study in smoking cessation where we're going to have people's stress level, their skin conductance. We'll have all these online streams coming from sensors, wearable sensors. Also, methods for constructing what we're calling a treatment policy, that is decision rules that link the context, the time of the day, how you're feeling to whether or not you should get an intervention. And then how you can use algorithms to update that as time goes on. this involves a lot of computer science, a lot of algorithmic development. This, actually, there's some really interesting statistics because the parameters are all non-regular parameters. And how do you do inference for non-regular parameters? It's a challenge. I just wanted to, this is my last slide, I wanted to just tell you who's on our team. At least this is part of the team, actually. Hung is the grad student who suffered. Andy and Cyrus are they're not anymore, but they were undergraduates in computer science. They did all the programming of the apps. It's amazing. This guy now has a startup company with the apps. And then Pedja is a human-computer interaction specialist, so how do you present information on the screen? And Ambuj is a computer scientist. So he, of course, is very interested in online learning, as myself. It's just that I have to do this other work first. And we had an undergraduate who did a beautiful sample size calculator that you can access via the web. It's the first round of it. We're going to make it even nicer, and you can access it here if you end up doing one of these studies. And that's it. Thank you.
Yeah, so you said you had some working assumptions of independence over time.
Right.
But you've got
they're not
contrast.
true.
I'm sorry?
They're not true.
Well, yeah, but your power should go up a lot if you've got the between subject contrast. That correlation diminishes power within subjects. It would increase.
And
So,
that's probably
aren't you
why.
missing that, or?
Well, I think that's probably why we have the robustness to that assumption. The reason why we made that independence assumption was so that we could simplify the non-centrality parameter, and we got these nice, relatively simple formulae for the sample size calculator. But we didn't suffer. I think we did not suffer precisely because of what you said. When you have more correlation, you actually get better power with the within-person contrast. So we didn't suffer. In fact, we had some simulations where our assumptions were violated and we got better power.
Yeah, so if I understood you correctly, you're sort of losing some here and gaining it back here.
Right.
It's evening out.
And it's, yeah.
Possibly.
Yeah, that's what we found.
It's clearly it worked. The other thing I wanted to ask was, it's a short study at first, but you're going for the longer term study down the road. And what you ultimately care about is what happens after the frustration period, after the learning period, etc. Does it make sense to base the test on all of the beta J's, on the early J's?
Yeah, you could have a run-in period, for example. That would make a lot of sense. Like the first week while they're learning to use the phone, you would just ignore everything.
Mm-hmm.
We've talked about that. I do want to say something about that year-long study. In that year-long, okay, so here's the plan. First, we run these micro-randomized studies. In secondary, we're going to test whether or not our intervention has any effect. Let's hope it does. And I'm doing this across several domains. Then what we'll do is we'll create a policy for matching the context to whether or not you should get an intervention. That policy is a set of decision rules. If you're used to control theory, it's a controller. It's from that area. And that has parameters in it. Then when we go to the year-long study, we'll be running something close to a stochastic gradient ascent kind of algorithm, a stochastic approximation algorithm, in very controlled manner, where we'll be changing the parameters of the decision rules of the treatment of the controller. That's the last study. So the last study will have randomization in the sense that we will never know for sure at any particular time whether or not you'll be provided a treatment or not, but the probabilities will become more and more, they'll become biased depending on what the evidence today is. And in fact, so if you show evidence of burden, we'll back off. The idea is that we're going to back off and leave you alone. So we want to have that. What we want to do is sort of, if you're familiar in engineering, there's this whole notion of tracking in non-stationary environments. We're going to be looking at that kind of setting. It turns out, I got to tell you, it turns out that there's just, this whole area is just ripe for statistics to me. You can really tell we have not been there. Because what's happening is in this field, in artificial intelligence, for example, all the theoreticians pretend like they're in a stationary environment. Then you go and talk to the people who are actually doing artificial limbs, it's control of artificial limbs, and they don't do any of the things they're supposed to do if it's a stationary environment. In fact, for example, they don't ever reduce the amount of randomization. They keep the amount of randomization forever. Why? Because they know they're not in a non-stationary environment, and they have to constantly be able to reassess whether or not the treatment is working for that person. And no one has mathematized this. No one has operationalized it. But it kind of gets it, maybe I didn't answer directly your question, but it tries to adapt to the fact that this person will change over time. And there may be periods when you can't bother them, and then other periods where you can bother them more and still help them. And that's the longer term idea. But the mathematics of this, posing the question, no one has thought carefully about this, and it's so obvious. There's this enormous disconnect between the applications and the theory. It's enormous. Yeah.
Question. These kind of studies, there is compliance when the study is going on.
The compliance.
Usually.
Yeah, compliance here is going to be them deleting the app. They're going to delete the app, and then we've lost them.
No, when the study ends,
Yeah.
in some obesity studies, what they do is they end the study and wait for a period,
Oh.
and then restart to see if they have been complying with whatever they've been asked to do during the study.
Right.
Because many obesity studies, when the study is going on, they're
They're
losing
fine.
weight and so on and so
And then as
forth.
soon as the study's up, okay, so let me tell you, I had a big discussion with one of there's this guy named Richard Sutton. He is extremely famous in computer science. He's one of the fathers of artificial intelligence. And I went to him, I was thinking this sort of thing. And I went to him and I said, look, what I want to do is he told me, but let's think about this. You and I walk around with watches all the time. Think about it when people first discovered the clock, and we didn't have to look at the sun and the moons to tell the time. Do you realize how upset some people were? Here we were depending on a clock to tell the time, and we were losing our ability to use the sun. We were depending on this device. We were offloading that low-level cognitive process of telling the time from the sun to a clock. He said, this is what this guy is telling the artificial intelligence guy. He says, look, what's wrong with offloading this low-level kind of behavior to the mobile device? Why do we have to believe that we're going to train people and then they're going to go off and be cured? No. He said, we need to develop supportive technology that they can offload low-level cognitive processing to that device for the rest of their life. For example, suppose you're a diabetic. Diabetics have to do around 21 self-care behaviors every single day of their life. Why should they have to watch the clock all the time? Why can't we automate most of that so they don't have to, this is low-level stuff. They could be so much more, they could be doing all kinds of great things with their mind. Instead, they're watching the clock and watching everything to make sure they manage their diabetes. Well, it's the same way with addictions or with other types. If there's a way for us to offload some of this to a device. Now, this is a dream, right? We're talking about a dream here. But that same guy told me he thinks in 5 years, a lot of our clothing will have wearable sensors. A lot of them. Already our tennis shoes, I don't know if you've noticed, but a lot of tennis shoes you can get with wearable sensors. So he doesn't see any problems at all. We can buy a little undershirt that you wear. Suppose you're someone who's having a lot of problems with cardiovascular heart failure. You could wear an undershirt that has a sensor in it that's monitoring the fluid in your lungs all the time. Instead of you having to be aware of how you're feeling internally. And if you go to the addiction field, and you're probably, because you mentioned behavior change, It turns out in the addiction field, it's a lot of people say everyone around the addicted person knows that the addicted person is heading for downhill before the addicted person does. This is exactly the kind of thing in which if you have a device that could be sensitive enough, could alert beforehand. He thinks we should not be training them to get off. He thinks we should be giving them something so they offload low-level cognitive processing to the device. You know, I offload, I don't know about you, but now I use my phone to drive. Like I travel all over, and I'm sitting there with my blue dot. I have completely offloaded my ability to get around town to the blue dot on my phone. And I bet a lot of people in here have. And 10 years I didn't. It didn't bother me at all. That was a long answer, I'm so sorry.
Well, let's thank Susan again, and we'll talk to you.